Alright, in this video we're going to look at a shift register. In the last video we looked at a parallel load register where we loaded a 4-bit register where all the bits got loaded at the same time. We could use a load control so that we could load the register with its previous contents if we didn't want to change the contents of the register, and we looked at an asynchronous reset. What here we're going to look at is where we have again a 4-bit register, but the information is shifted through this chain of flip-flops. So we only have one input, one data input to the flip-flop or to the register, and one data output of the register, and then of course we have the clock that's clocking the information in to the register. So the output of one flip-flop we have going into the input of the next flip-flop, that's our chain. The output of this flip-flop going to the input of the next, the output of 3 going to the input of 4. But they all have the same common clock. So if we wanted to look at a timing diagram for this shift register, it would look different than that of a parallel load register. So if we look at we have our pulsing clock, 50% duty cycle, and we have our inputs. These are the two inputs to our register, and we're just going to try to shift in one pulse of a data bit of 1, and the rest of the data bits being shifted in are 0. So that we have a pretty good setup and hold time to this rising clock edge into this first register. So after that clock edge and a little bit of propagation delay, this signal X is going to rise. It's going to become equal to SI, that serial input, and then when it will stay there until the next clock edge where it's going to sample a 0. So then after a bit of propagation delay, it's going to go back to 0, and then X is just sampling in a 0 because that's what serial in is. So X is what's our input to our second flip-flop. The output of that second flip-flop on the signal line is Y. So how does Y change? Well, Y is going to change to a 1 when it samples on this clock edge. This register is going to sample X equal to a 1. On this clock edge, it's going to sample X equal to a 0, so it's going to go back to 0 again. And again, we're showing that little bit of propagation delay at the output of the flip-flop before it changes after the rising clock edge. That's our propagation delay. So on this clock edge, Y, this third register samples Y being a 1, so with a little bit of propagation delay, Z becomes a 1. And then on the following clock edge, we have on this clock edge, the fourth register samples Z being a 1, and serial out becomes a 1. So it takes us here, we can count them, there's 1, 2, 3, 4 clock cycles to get this bit here, right, that 1, before that 1 comes out at the output. So the propagation, what's clear here though, from a timing perspective, the propagation delay of the flip-flop itself must be greater than the hold time of the flip-flop. So if we look here, this is for this second flip-flop, we have plenty of setup time. We have that little bit of hold time. That hold time is the propagation delay through this flip-flop that's holding X 1 for enough time to get to satisfy that we meet the hold time of the second flip-flop. So that's a key thing in our timing diagram. So again, this simple shift register. It has no clock control. It doesn't have any reset. It's constantly shifting this data in and shifting that data out. So what if we wanted to add some clock control? Well, we said we should not gate the clock. It's not good practice, but under controlled circumstances, like we have here, we're going to look at an example of gating this clock. So our clock is gated through an AND gate with this shift control. So if this shift control is 0, the output of our AND gate is going to be 0. If the shift control is 1, the output of AND gate is going to be whatever the clock is. And so that's the clock that that's the CLK that we're sending to each of these shift registers. And again, inside our shift register is just our simplest shift register, 4-bit shift register. So one of the things we do want to be careful of, though, is when we are gaining a clock that we don't create a glitch, because if we get a glitch, if we get an extra rising edge, that's going to disrupt our timing. So the shift control and clock can't transition at the same time. That's one of the things we have to be able to make sure of if we're going to gate a clock, or we'll have a glitch. Since it's an AND gate, if either input is 0, the output is 0. So we want to change that shift control when the clock is equal to a 0. That way we can change the shift control and our output of our AND gate will still be a 0. So that's a key concept here when we're gating clocks. I think there's a homework assignment that uses a NAND gate for the shift control. So then you have to consider with a NAND gate, when can you change the shift control so as not to affect the output of the NAND gate. So in this case we have an AND. So again, once the clock is low, the shift goes high. When the clock is low, so we get a synchronous signal. And this is what our CLK signal will look like. We just let our shift control allow 4 cycles of clock to go through, and we call that T1 for cycle 1, cycle 2, cycle 3, cycle 4. And we do 4 cycles of the clock. So let's look at an example here. If we have these 4 cycles of the clock, if we started out, the contents of register A had a binary 6, the contents of register B had a binary 8 in there. After 1 cycle, our first clock edge, that first cycle, so if we look at this rising clock edge here, what's going to happen is everything's going to shift, right? So we have the output of register A going into the input of register B, so that's going to go there, and each of these are shifting over. So we get a 0, we get a 1, we get a 0, and we also have the output of register A is coming back around to the input of register A. So this one is also coming back around here. So this one is going here, and then we have a 0, 0, 1. And then that's going to repeat itself. So we're going to get, if we look, this one is going to go 1, 0, 0. This one's coming back around, right? So that's a 1. It's also going here, 1, 1, 0, 1. And now we're going to get a 1, 1, 0. This 0 is what's coming back around. So you get a 0. The 0 is also going here, 1, 1, 0. So we did end up with this 6, binary 6 in register B. We also ended up with this binary 6 back in register A, because that's what we did, right? We took it out, we shifted out, and shifted it back in again. We also shifted it into register B. So again, so that takes 4 clock cycles to shift 4 bits of data, whereas if we had 4 bits of data to load into a parallel register, we could do that in 1 clock cycle. So the difference between parallel and serial operation: parallel mode, several streams of data transferred over multiple channels. So since we have to have multiple channels, these could be wires. If we just imagine we have all these wires running next to each other, whether they're on a board or in a conduit. We have the opportunity for crosstalk between these channels, and that's one of the problems with parallel mode. But certainly the advantage is we can load a whole lot of registers at once, so we only take 1 clock cycle to do it. Serial mode, we have 1 stream of data or 1 channel, so we don't have the opportunity for crosstalk. For register to register transfers, though, we need n clock cycles, and so it's dependent upon how many bits we have in the register. But it does require less equipment, so it can be cheaper. And it can actually, we can transfer data serially at a much higher rate, a higher frequency, or more quickly. Partly because crosstalk's not an issue, and partly because typically serial mode is done asynchronously. That's why we gated the clock there. And so clock skew is not an issue. And so additionally, if you think about an integrated circuit and you think about, how many pins you can have on that integrated circuit, we looked at in lab, we used a lot of 14-pin ICs. It could be 16-pin ICs, but if you wanted to transfer in, just for an 8-bit register, that would require 8 of the I/O lines. A 16-bit register, 16 I/O lines. So it helps to minimize the number of I/O pins required on an IC as well. All right, that's it for this video. We'll look at some examples in future videos.